people. I don't take it as an indictment on me, but all right. Well, anyway, happy Monday. Welcome to week 4. And I hope your classes are going well. I know a lot of people have midterms and stuff. But anyway, here we are. We're continuing more stuff in Python and more stuff on Numpy. So on Friday, we brought up Numpy. Numpy, kind of the module or the library that we use that gives us the array data structure, right? And the array, I don't remember if I talked about this on Friday. The reason why we want to use arrays rather than lists is that just arrays are computationally much more efficient than lists, because within Python, as far as its memory structure goes, inside a list, you have to keep all of this kind of additional information that says, like, okay, this value is a float, and this value is a Boolean, and this value is a string, and all of that kind of information has to kind of sit somewhere in the array, or somewhere in the list. Whereas when you have an array, when you say, okay, every single value in the array is a float, you don't have to keep track of all of that. And so just computationally, arrays are a lot more faster as far as computations go. And we'll see a little bit of that in today's lecture. And it's a big deal, especially in data science and, kind of as we start crunching with big data things, to have kind of that computational efficiency. And I would say that's probably why Python, like in industry, Python's like much more popular than R, which it's a little like, I feel a little bit bad for R, just because R was, from the start, always centered around data, right? It was always history lesson that nobody asked for, right? So you go back, several decades, all of the major research for kind of computer science was happening, do you guys know where? In Bell Labs, okay? So you think about like where the major research for computer science and AI and stuff, what do you guys think of? You think of like places like Google, maybe Tesla, Facebook, Apple. These places are like kind of on the cutting edge. And a lot of this happens like in industry and also kind of with partnerships with academia. And so you think of like, universities doing these kinds of joint things. You go back, 60 years, the cutting edge research was happening at Bell Labs. Bell Labs being kind of the V1, the research division of basically the one communications network, right? So basically all the telephone lines were controlled by like the Bell company. And then it got split up, and now and then it's like remerging, and you got AT&T and stuff like that. But basically, the research division was Bell Labs. They developed C, and they developed S. So C was for the computational, computer programming, and that eventually becomes C++, and all of these kind of C derived computer languages. And then on the other side, you had S, which was from the start developed by statisticians in order to kind of handle data and things like that. And S eventually turns into R, and so that's what we have. So R, its history has always been centered around handling data, and whereas C and all of those kind of languages have always been centered around computational efficiency. And so that's why you have these languages. All right, Python comes down much later down the road as kind of this higher level general purpose programming language where you don't have to do all of the things in C++ and stuff. And I don't know if any of you have taken like Pictene, where you have to like declare all of your variables, and if you haven't, don't worry. But it's a headache, right? You have to be like, oh, I'm going to make this bucket, and it's only going to contain integers, and if I ever try to put something other than an integer into it, it's like, compiler error, blah blah blah, And so, Python's like, you know what? let's just have the language take care of all of that stuff. And so you have that. R is also kind of developed around like, okay, we don't want to be like computer scientists. We just want to focus on statistics and data. And so, everything was kind of developed around that. Python wasn't originally developed for, statistics and data science, but with packages like Numpy, it was like, oh, you know what? We can handle data and we can do things, pandas come along and we're like, oh, you know what? This is actually pretty good and it's faster than R. And so, now that when you have like these huge data sets, Python is often the more popular choice for these things. That said, as far as like classical statistics analysis, like if you want to do linear regression, you can do it in Python. You have stats models, you have sklearn, which is great. But you want to do like a traditional linear regression thing, it's hard to beat R. All of the things built into R and all of that. And then I'm also highly biased in this matter, but like as far as data visualization, I think it's really hard to beat ggplot as well. Python has matplotlib, and then I think there's a lot of there's kind of like this confluence of the two. Like you're starting to get like RStudio now like supports Python and almost at a native level, and you have this reticulate package that you can just hand off variables within your R environment off to Python, and then pick up those variables from Python and hand them back to R, and kind of like switch between the two and get the best of both worlds. And there's kind of this merging of the two. My sense, though, is that when you enter data science, you're going to have people coming in from kind of the statistics side. You're going to have people coming in from the computer science side, and right now it feels like the computer science side has a little bit more, pulling power, and they're pushing Python down everybody's throats, and it's not a bad thing. Python, I'm teaching Python, and I love this stuff, but I also feel like, poor R. But anyway, here we are. We're talking about Numpy. Numpy has really allowed for Python to really get into this kind of data science space where we're handling large amounts of these huge arrays efficiently, and you have these tensor basically is just a big array, and all kinds of computations there. So anyway, it's important that we can get into Numpy. So what do? We start off importing Numpy as NP, and here are a few operations that we can do. So let me go ahead, and I'm going to just create two arrays here, X and Y. So one is going to be 0, 1, 2, 3. The other one's going to be 100, 101, 102, 103. And what you can do is you can use this operation called concatenate. Okay, concatenate is going to join them, and it's going to default to joining along the axis. Okay, so let me go ahead, and I'm going to concatenate these two arrays. Okay, and this is what it does. What are the dimensions of this array? 0, 1, 2, 3. What are its dimensions? Yeah.
4 comma.
4 comma, right? It's 4 comma. It's one dimensional. Okay. So this is 4 comma and this is 4 comma. So when you concatenate two things that are one dimensional, it's just going to get longer and it's going to become 8 comma. Okay. All right. So you can specify which axis that you want to kind of concatenate along, right? So you can say axis 0, meaning which dimension, the 0 indexed thing, which is 4, right? 4 comma. And so, you concatenate along that. If I try to say, concatenate along axis index 1, okay, it's going to throw an error because there is no axis index 1, right? So you look at the shape, of x, and it's 4 comma, and so there's no, this is index 0, which is the 4, and there's no index 1 here. Yeah, question?
When you run the concatenate function, is putting the x and y in brackets like anything? If you didn't have any brackets, would it change anything?
You basically hand it a tuple, or I mean an iterable. So it could be brackets, or it could be you could put it in parentheses. So you hand it an iterable of either a tuple or a list of the things you want to think. Here, let me just double check. Okay, np.concatenate. So I can do parentheses tuple xy, and that's no problem. I think. Well, I don't know. Will this work? Yeah. So it doesn't. It won't let you do it if you don't put the items together into an iterable. Okay. So if you want to make a two-dimensional array, you got a 2x4. You can use VStack. Okay, VStack will do probably what you're looking for, and that will do that. What you can also do is you can reshape x into a two-dimensional array and reshape y into a two-dimensional array, right? So these are two-dimensional. This is now a 1x4. Okay, and so if I put those things and I concatenate along axis 0, now they get stacked, because if you think about what's the shape of x after reshaping, the shape is 1x4. And so here, when we concatenate along axis index 0, it's joining the 1 and the 1 to make a two-dimensional, not two-dimensional, 2 rows, okay? So it's joining these, right? If I say concatenate along axis 1, it's going to look at the 4 and the 4, and it's going to add those two together. And so now we will get 1 comma 8, and we get this two-dimensional array with dimensions 1 by 8. Right? Does that kind of make sense? The axis 0 here, once we make it two-dimensional, stacks the rows. Okay. Whereas when we had one-dimensional axis 0, there's only one axis 0. It just makes it length 8. Okay, so here I've got X matrix, 2 rows, 3 columns, and here's another matrix, 2 rows, 3 columns. Okay, so I've got a 2x3 and a 2x3. So the shape of XM is 2x3. The shape of YM is 2x3. All right, what is the resulting dimensions? What is the resulting shape if I concatenate XM and YM? So the default is going to concatenate along axis 0. So what are we going to end up getting? Are we going to get 2 by 6 or 4 by 3? Axis 0. So axis 0 means we're going to add index 0. All right, so 2 and 2, we're going to add those, and we're going to get 4 by 3. Okay? So, so if I do that, and if I specify axis equals 1, we're gonna, axis equals 0, we add basically, the 0 index is the 2 and the 2, we add those two together, so we're gonna get, this is exactly the same. The default behavior is concatenating along axis 0. If I specify axis 1, concatenate along axis 1, we're gonna take the index 1 position, which is the 3, and the 3, we're gonna add those together, and we're gonna end up getting a 2 by 6. Okay? So you think about what are the shapes, what's the shape of X, what's the shape of Y, and when you concatenate, you're basically adding, for index 0, you're adding the index position 0, 2, or axis 0, your index position 0, which is the 2's, or axis 1, you're looking at index position 1, you're adding the 3's together. Okay. You can also do VStack and HStack. All right, so VStack just stacks them vertically. HStack stacks them horizontally, and it, this also works fine, right? Okay, math operators. So here's x and y. X is 0, 1, 2, 3. Y is 101, 100, 101, 102, 103. And you can say add 5. So that's just going to add 5 to every element. You can take x and add y, and it's going to do element y's addition. So 100, 0 plus 100, 1 plus 101, 2 plus 102, 3 plus 103. You get that. X times y does element y's multiplication. So 0 times 100, 1 times 101, 2 times 102, and 3 times 103. Okay. When you do element y's multiplication and add them up, you have two vectors and you do element y's multiplication, you add them up. What do we call that? We call it the dot product, right? So you can do that, x times y, and you can sum it. Or there's also the operator, the dot product. Okay, you can do np dot dot, and that's going to give us the exact same value. And then there's also the matrix multiplication operator, and you can do the matrix multiplication operator is the @ sign, and technically with matrix multiplication, one has to be a row and one has to be a column. But if you give it one-dimensional arrays, it's going to know what to do, and you will also. So all of these things result in the same, right? Basically, you're multiplying the elements and you're adding them together. So all of these, you get 0 plus 101 plus 204 plus 309, 614. Okay, you have the matrices. I have these 2 by 3 matrices. And same thing, I can add 5, and I'm going to add 5 to every single element in this matrix. 0, 1, 2, 3, 4, 5 plus 5 gives me 5, 6, 7, 8, 9, 10. Okay, element-wise addition, no surprise here. 0 plus 100, 1 plus 101, 2 plus 102 for that top row, 3 plus 103, so on and so forth there. Okay, just to see it again, you have element-wise multiplication, and this is no surprise. Okay, 0 times 100, 1 times 101, 2 times 102 for that top row, 3 times 103, and so on for the second row, and we have that. Okay, you also have np.multiply, which is the exact same thing. Element-wise multiplication, you get the exact same thing. So you have the infix operator, which basically just allows you to kind of do stuff like this, and you also have the function to call it with arguments in case you need to pass different values to the function as well. Okay, so you have that, right? Okay, and then you have, so if you want to do the dot product, dot, basically if you want to do matrix multiplication, you'd have to transpose. You have to transpose, so I'm going to do y matrix transpose, so that will become a 3 by 2, and the result will be a 2 by 2, so I'm going to do a 2 by 3 multiplied by a 3 by 2, and the result will be a 2 by 2. Okay. You can also call the dot operator from the array itself. So I've got the two functions. I've got numpy.dot basically dot multiplication, xm times ym transpose, or you can just do xm dot ym transpose, right? So you can do it's hard, it's funny to read, right? xm dot ym dot t, right? It's like there's a website called /dot, and the full address would be http:///dot.com. Anyway, so xm dot whatever. Okay. All right, and then you have the infix matrix operator, xm @ sign, or matrix multiply ym transpose. Okay, and then what would happen if I didn't transpose? Okay, we get an error. It just says you've got a dimensional mismatch, right? Because it's saying, when you do matrix multiply, it's got to be, you got to have an n by k, and this k needs to match the number of rows, right? The number of columns in matrix 1 needs to match the number of rows in matrix 2, and here, I mean, what a friendly error message, right? And it's like, you've got size 2 is different from 3, and you go, oh yeah, I did this wrong, right? versus like, as far as error messages go, they're helpful. Okay, a lot of times, not always, but a lot of times they are. All right, let's do some more math. So right now here I've just got lists, right? I've got lists, and I can take lists and I can add and subtract and multiply and divide and do the negative sign on these things and the power and modulo division and absolute values, right? So these are all kind of just, this is base Python. I haven't done, I'm sorry. This is not base Python. This is with the Numpy array. These aren't lists. I'm all confused. Okay, and so you can just do all of these basic operations with Numpy arrays. I don't think any of these are a surprise to anybody. Everything behaves exactly as one would expect, right? As far as you have the array 0, 1, 2, 3, and what happens if you add 4 minus 5 multiply by 2 divide by 2 or anything like this. Okay, I guess one thing to note is that all of these operations, because we started off with integers, pretty much all of these operations result in integers with the exception of the division, right? The division turns everything into floats, but everything else, it's like, oh yeah, I got an integer, you want to square that, you're going to get integers back, okay? So no surprise there. You have trig functions, and so if you want to access trig functions, there's a couple ways to go about it. One is you could import the math module, but when you import the Numpy module, Numpy has a bunch of math functions built in as well, okay? And it also has like math constants that aren't part of base Python. So like the pi constant is built into Numpy. It's also built into the math module. It's not built into base Python. So anyway, here I'm going to say I want 0 through pi, and I want 5 values. So we're going to get 0, pi over 4, pi half, 3/4 pi, and 4/4 pi. And that's what we have, okay? Or at least the floating point approximations of these things. And then we can say, all right, what's the sign, right? And so you get 0 and what is this, root 2 over 2? Is that right? And then 1 and, so on and so forth. Back to 0. And again, anytime you see something to the 10 to the negative 16 as a floating point number, that is basically, it's basically 0. It's just a limitation of floating point arithmetic. So it should be 0. It's just, stuff happens, right? Okay. Cosine, you go from 1 to negative 1. What are we going to see when we see tangent? Okay, well, we don't get infinity. Okay, we get 10 to the 16. Again, that's very much not infinity, but it is a big number, and it's, again, floating point arithmetic limitations. So it does, it shoots off to something close. I mean, not close to infinity at all, but bigger than most other things that we would operate with. Okay. Yeah, the idea of getting close to infinity is just, I guess it never exists, huh? My daughter asked me, "What's the biggest number you can think of?" And I said, I can't even think of the biggest number, right? Like, it's just a weird thing, right? What's the biggest number you can think of? I don't even know. Okay. You got log functions. Are we used to just accepting that anytime we see log, we're talking natural log? Okay, that's just how it kind of goes, right? I know, like in high school, we always teach you ln, and then log is the common log, but like once you're in college, it's like kind of the opposite. We always use log for natural log, and then common log is log 10. But that's how it goes. Okay, so you have that. So you have the log, and you have the e function, and exp2 is 2 to the y, so that if you need binary powers, and then if you want like just some generic thing, Okay, you have the power function, and that's just any value raised to y, and you can put in any of these things as what was it? Just basically any array, and all of these are vectorized or array things, and the computations are quick. Okay, I forgot. Let me give you your view quiz answer. First one today is, what is it? B. B as in bear. B as in bear. His first view quiz answer. B as in bear. Okay. There is, in base Python, you have the sum function, okay? And it does exactly what you would think it does, is it adds up the numbers, okay? And then in NumPy, you have the numpy.sum function. If you're going to load in NumPy, probably use the NumPy sum function. You're going to get better performance, okay? But it does stuff a little bit different, okay? So here is this array, 0 through 99, okay? And then what happens when you add them all up? What is it? N times n plus 1 over 2. That's the shortcut for like adding up all the integers, right? So you get 4950. It adds it up, okay? NumPy.sum, you get the exact same value. So there is this, what we call a magic function in IPython, and this is called, it's called timeIt. And basically, you give it an operation, and it will time how long it takes. And it runs it like 100 times or something. You gotta sit and wait like 30 seconds for your computer to do this. So here it's gonna run the sum operator using base Python, and then it's gonna do the numpy.sum operator using NumPy's function. And NumPy's function is just way faster, okay? So for the sum operator, it's 1 millisecond per loop, and for the NumPy operator, it's like 10 microseconds. So what is that? 100 times faster? Okay, so big performance difference. Okay, similarly, you have you can ask for min and max. Okay, on this big array. So if you ask for 10,000. This is like what's the distribution? I forget. The Gumbel distribution? I don't remember. So it's like if I pick random numbers from 0 to 1, okay, and if I pick 10 of them, what do you think the largest value is going to be? Okay, I mean, we don't know, right? But, there's a probability distribution, right, with probably like something around, I don't know, 0.9-ish being like more common, but you might get 0.9999, and also it's possible that even after picking 10 numbers, your largest number is like 0.5, right? And so there's a distribution for like the extreme values in some kind of thing, and that's how they figured out how many tanks that the Axis powers had, right? Do you know the story? They're like they were trying to guess like how many during World War II, the Allies, they wanted to know the how many tanks the Axis powers had, and so what they did is they looked at like all of these tanks that they defeated in battle, and they looked at the serial numbers, and they said, okay, you know what, the largest serial number we've seen so far is this, and this is based on how many tanks we've encountered so far, and based on that we can kind of extrapolate to assuming that the serial numbers are kind of sequential, so if you've blown up like 50 tanks and the largest serial number you've seen is 117, how many tanks total are there and stuff like that. Statisticians saved the day, right? And they came up like within really close to what the actual values were. Okay, but anyway, there's some distribution. So the biggest and smallest values you've seen, and after selecting 10,000 values is this. And then you have Numpy versions of min and max that give you the same values, but again, operate at different speeds. So 639 microseconds versus something in the 8.97 microseconds. Okay, but the operator, the sum operators work different when you have matrices. Okay, so here I've got this matrix with the numbers 1 through 11. No, I'm sorry, 0 through 11. Okay, arranged in a 3x4 matrix. And when you call sum, it's going to give you column sums, which I think is a little bit unusual, but that's the default behavior of the base sum function. Basically, it sees this as almost like a list of 3 things, and then it's adding those 3 lists together. Okay, so it sees basically an array of 3 arrays, and it's adding those 3 arrays and it's returning that. So it's going to give you 14, 369 is 18, 408 is 12, and so on and so forth. When you call numpy.sum, it sees it as one array, and it's going to give you the sum of all the values in the entire array. Okay, so that I don't think that's numpy.sum is probably what we would expect. Okay, if you want to sum along some axis, okay, we can do that, right? So I could say sum along axis 0. Okay, so again, the shape of this array is 3 by 4. Okay, and so when you say sum axis 0, it's going to take the 3 by 4 and it's going to collapse the 3 into a 1. Okay, so when you say sum, you're going to take, you've got 3 rows, and we're saying collapse the 3 rows into 1. Okay, so you get 1 row, and it takes the things, right? When you say sum along axis equals 1, okay, it's going to say you got 3 rows and 4 columns. Axis 1 refers to the 4 columns, and it says take those 4 columns and collapse them into 1. So when you do a sum, you're taking a bunch of numbers and collapsing them into a single number. So, or anytime you do some kind of summary function, you're taking multiple numbers and collapsing it down into one number. So when you say axis 1, you're saying 3 rows, 4 columns. Axis 1 references the 4 columns, collapse the 4 columns into 1, and so you're going to get basically row sums, 19, 14, and 33, right? And this is a one-dimensional array. Okay. Same thing, you can call for any other summary function, min, max, standard deviation, anything that's going to take multiple values, return a single value. You can specify the axis along which to collapse. Okay, so you get print m, standard deviation of m will be the standard deviation of the entire matrix. Okay, or you could say I want the standard deviation along axis 0. So collapse the rows, collapse the 0 index dimension into 1, and we get 4 standard deviation values, basically the column standard deviations. Or axis equals 1, collapse the columns into 1, and now you get basically row means here. Same kind of thing along here is higher dimensional thing. So here's a 3-dimensional structure. Okay, 2 sheets, 3 rows, 4 columns. Okay, 2 sheets, 3 rows, 4 columns. What will be the dimensions or the shape after I do np.sum a? What is my shape, and how many? What's the value going to be in every cell? Because everything's a 1. So your answers are, you're going to see a bunch of 2s in a 3 by 4, or a bunch of 3s in a 2 by 4, or a bunch of 4s in a 2 by 3. So axis 0, what are we collapsing? Yeah.
3 by 4.
Yeah, we're going to see a bunch of 2s in a 3 by 4. Okay? Okay, what about axis 1? So we're collapsing axis 1. So we're going to get a bunch of 3s arranged in a 2 by 4. Okay, and then this one will be the last one, right? So we're looking at axis 2, right? So we got the 2 by 3 by 4, so we're going to collapse axis index 2. So we're going to see a bunch of 4s arranged in a 2 by 3. Okay? Does that kind of make sense? It's good to review and make sure you understand how sum, doing any kind of sum operation across a particular axis works. Okay, next view quiz answer is E. E as in elephant. Second view quiz answer. E as in elephant. Okay, how do we deal with missing values? Actually, this is technically not missing value. You have nans, okay? So nan is not a number, and that is built into floating points. Like when you have floating point numbers, you have a way to have infinity and negative infinity, and also things that are not a number, which is like what happens if you do like infinity minus infinity, or infinity plus negative infinity. You get like an indeterminate result. You get nan. Okay, and we use nan as a way also for missing values. Okay, and you can create nan by doing float nan. All right, and it will say, okay, that's a nan. But nan, okay, not a number. Nan is always going to be type float. Okay, nan is also always going to be type float. Okay, you can also create infinity directly, and you can do float INF for that's going to create the floating point representation of infinity. Again, it's not really infinity. It's a shorthand way to represent infinity, and if you do operations with infinity, like infinity divided by infinity, you get nan. Infinity minus infinity, you get nan. And the floating point systems, just this is what it gives you. Okay. If you try to add nan to a number, like what is the sum? I've got two numbers here. This number is 2, and I don't know what this number is. And I'm going to add them together. What's the sum? Okay, the answer is like, well, I have no idea, right? Because if you don't tell me this number, there's no way I can tell you the sum of those two numbers. So the default is when you do sum with a nan, you're going to get back a nan. You're going to say, well, if I don't know this number, I can't add 2 to it and tell you what the result is. Okay, now all of these functions have what we call a nan safe version, which just says, okay, if you have missing values, just ignore them. Okay, just ignore them. And in R you had something similar. You had na.rm equals true, and this is kind of the thing. So this just says, okay, if we're gonna just ignore missing values, and if you got a 2, then the sum of the non-missing values is 2. And so you have all of these things, right? Sum, product, mean. I don't know anything here that's surprising. No, I don't think so. Okay, you don't have nan safe versions of any and all, which are basically your Boolean versions. Okay, broadcasting. Broadcasting is kind of this idea of like recycling values. So here I've got 2 arrays of length 3, and when you add them together, it's no surprise you get they add them element wise. Okay, in R, for better or worse, R does like incomplete recycling, right? So if you do like a vector of length 3 and you add a vector of length 2, like it'll match the first element, the second element, and it recycles around and adds the first element to the third element. And that's just what R does. It gives you a warning, and it says like the shorter vector doesn't match the length, is not a multiple, or the longer vector length is not a multiple of the shorter length or something. It gives you a warning. Python just says no, I'm not going to do that, right? These are incompatible. You've got a length 3 and you got a length 2. I can't broadcast this. Okay. If I have a 3 by 3 matrix and I've got this length 3 one-dimensional array, I can take this, okay, and I'm going to broadcast it, okay. And so I can take A, 1, 2, 3, and And what it will do is it's going to say, oh, you know what? The shape of E is 3 by 3, okay? And we're going to have to add 1, 2, 3 across the first row, 1, 2, 3 across the second row, and 1, 2, 3 across the third row, okay? We can also reshape A into a column, and if I take E and I add this column, okay, then it also does that, okay? And so basically it's going to recycle this column and add it across the columns. So now I get 2, 2, 2, and 3, 3, 3, and 4, 4, 4 reading across the rows. Okay. All right, here's another example. D is a 2 by 3 matrix. A, again, is this one-dimensional array. And I get, and if I do D plus A, it's going to broadcast. It's going to take this one-dimensional, it's going to do it to the first row, add it to the first row, and it's going to add it to the second row. Okay. If I have a vector of length 2, and I add it to D, Python is going to complain, okay? And it's going to say, all right, C is length 2, and D is 2 by 3, and the default, it wants to kind of do it across the rows, right? So it says, okay, you know, you look at C, and I don't like what you're trying to do here, okay? But what I can do is I can take C, and I can make it a column. I can reshape it into a 2 by 1, right? And this works fine, okay? So I've reshaped C into a 2 by 1, and now I have a column, two rows, one column, and I can add, 7 across the top and 8 across the bottom. So, so anytime you do some kind of operation, Numpy will often kind of warn you and say, I don't like this weird mix-up that you're trying to do here. Okay. Let me see, what else do we have here? Okay, so this is kind of the thing that maybe surprises people a little bit the most. Okay, E is 10 by 1, and F, well, I guess it's just length 11. Okay, and we can add these. These are compatible, right? So what it's going to do is it's going to broadcast E. It's going to say, okay, well, F is length 11, and E is 10 by 1. So it's going to broadcast E into a 10 by 11, and it's going to broadcast F into a 10 by 11. And so it creates a 10 by 11, and both of them get broadcast into kind of larger things, basically recycled into larger things, and then it adds them together. So if you give it these one-dimensional or column values, right? So here's 10 by 1, and here's it's not 1 by 11, it's just length 11. It'll do that. It'll broadcast just fine, okay? You can do it with multiplication, and this is basically your times table that, I don't know, you probably had to make in 3rd grade or something. And so you have that, and that's that, okay. We can take D, I can reshape it into a 1 by 6 and a 6 by 1, and, same kind of thing. We reshape it, we broadcast these things, and it goes. All right, I've got a few more things, but I think we can get through this. And you can also just look at the notes yourself. Let me just give you your last view quiz answer. Last view quiz answer today is A. A as in apple. A as in apple. A. Boolean operators. So these are all kind of things that result in trues and falses. All right, so here I've got 0, 1, 2, 3, 4, 5, and I can just do is x less than 3, and we're going to get basically an array of trues and falses, right? You got less than, greater than, or equal to, exactly equal to 3, and stuff like that. You can take these results, this Boolean vector of trues and falses, and then you can subset your arrays using this Boolean vector, right? I think if we all took Stats 20 and we all used R, we're very familiar with this kind of subsetting using a a Boolean vector. So I think I can fly through this just fine. Okay. The one thing that I think people, and then you can also throw a Boolean vector into a function like sum or mean, and it converts them into zeros and ones, and it gives you, the count of trues or the proportion of trues. One thing that you have to get used to is the negation operator is the tilde, not the exclamation point, okay? So if you have like x equal 3, you get a Boolean vector, and then if you want the flip side of that, then you use the tilde rather than the exclamation point. So that's just something you got to get used to, okay? What happens here, right? Okay, this is, I just get false everywhere. So if you leave off the operator, all right, so what was x? X is, 0, 1, 2, 3, 4, 5. And if you do the negation operator on this, you get like, wait, now I'm confused. Oh, wait. Hold on. No? Yeah, okay. I'm not sure. Yeah, so the negation operator applied to integers, what is it doing? I'm not sure, 100%, okay? It's best used for Booleans, and it's doing something here. I gotta look up exactly what's going on here. Why we're getting -1? Yeah. Okay. Well, anyway. So just make sure that you apply the negation operator to something that's Booleans and not like an integer or something. Okay. You can also do Boolean operators to matrices, and you'll get a matrix of Booleans, and you can still apply, your sum functions, and then with sum functions, you can also apply, sum over this particular axis or that particular axis, okay? And then you have the bitwise operator, which just basically allows you to do like your and statements and your or statements. This is different. So in Python, we have the and we type out A and D, and we have the or, and we type out or, and we kind of use those in like your like if statements, okay? And you have these conditions, and you're looking for stuff like this. These bitwise operators will take arrays and will allow you to kind of compare, or not compare, but like do and or operators and return a vector of trues and falses. Okay, so here I have A and B, which is vectors of trues and falses, and we have the bitwise and so this will do element-wise comparisons, and it will look for true and true, true and false, false and true, false and false, and so we're going to get this vector or this array, true, false, false, false. Okay, same thing with the or. This does element-wise things, right? If I tried to do, say, like A and B, okay, this says I can't do this, right? It doesn't like, so if in if statements you would use the and operator, not the ampersand. Okay. Okay, you have the exclusive or as well, and then the negation is the tilde. Okay, that's the bitwise not, I guess. Right? You have the any and you have the all, and this will take the entire array and say, are any of the values true, or are all of the values true? And that works just fine. Okay, fancy indexing. Basically, if you wanted to just pull out elements index 0, element index 1, and element index 5, you can do that, right? So element index 0 is 37, element index 1 is 12, the fifth element is index 5 is 5 there, okay? And similarly, you can ask for, take these things, and I can say, give me X arranged, the index. So I can say the first index 1 and index 2, and so on and so forth. And so if I subset x using an array of indices, I'm going to get an array of those values, right? So I can do that as well. Okay, well, we're out of time here, but I'll just have you read the remaining examples. I hope they're clear enough for you to kind of make sense of what they are. And again, if you have any questions, I'm happy to answer them as well. But we'll go ahead and just end here for today, and I'll leave you to read the remaining kind of examples on your own time in the notes. Okay, have a great day. We'll see you on Wednesday.